All right. Okay, so today we'll take a look at rejection sampling, and I had more slides and stuff, but for whatever reason I can't knit them right now. So I gotta fix this at some point, and I honestly don't know what's going on. So anyway, we'll do our best. We'll do our best, which is all that we can ask for. I'll figure this out and I'll post up the notes. So. Okay, but all right, so let's talk. All right, so rejection sampling is another method for generating a random sample. So we started off talking about Monte Carlo integration early on in the quarter, and that technique requires the ability to generate values from a given distribution. And generating values from a given distribution is pretty easy if you have a well-known distribution like the exponential or the normal or whatever, because, and I have to talk about the midterm. Yes, thank you. I'm like, my mind's all over the place. Okay, so all right. Let me just finish talking about this, then we'll talk about the midterm, and then we'll go back to rejection sampling. We might not even get to the slides I wanted to show you, so maybe it was all for naught. Okay. Okay, so anyway, so rejection sampling is another technique that allows us to generate values from a given distribution, random values from a given distribution, which is kind of a key and central idea in kind of Monte Carlo methods. And we saw, like, at a very basic level, like the linear congruential generator for generating random values from the uniform distribution. And we're going to say, well, okay, if we can generate random values from the uniform distribution, or at least pseudo-random values from the uniform distribution, can we then generate values from other random distributions? And we saw, InverseCDF, and InverseCDF is a very effective method. And then, and today we'll do rejection sampling, which is another way to generate values from going from a random uniform to basically any other distribution. Okay. Now, a lot of this has been kind of made a little bit redundant because R has these really great features built in, right? But it's kind of almost like like if the computers broke down or something, right? Like if suddenly, like, you had to work on some old computer workstation that didn't have R, and you had to generate your own random numbers, like, at least I showed you the linear congruential generator. It's not like the greatest performing random number generator, but it kind of works. And then you could then also develop all of these things to generate your own random numbers. All right. Yes, let's talk about the midterm exam. Okay, so this is what I've come up with, and I'll put this up on CCLE. Okay, so the midterm will be on Monday, and it will be timed. It's 1 hour. Exam is open note and open book. And you can look at Wikipedia. You can look at the R help files. I'm going to lock up CampusWire, like, for the whole day. And then, and students are not allowed to, talk to each other. I think that goes without saying. Okay. So you'll log into Zoom and you'll turn on your cameras and keep yourselves muted. Okay. And I'll have 2 exams scheduled. You can either take it at 10 a.m. or at 10 p.m. and that should cover everyone globally. So at least one of those times would work for you. So this is 10 a.m. and 10 p.m. California time. Okay. And you don't need to tell me when you're going to take the exam. Just show up and we'll go from there. Okay. The exam will be a mix of pen and paper and a little bit of R scripting. Okay. And I think what I've written will fit within an hour. Okay, I'm not asking you to do anything crazy. Just I think it'll fit in 1 hour. So you will scan the pen and paper portions, and you know, using your phone, or if you have a scanner, you know, you'll scan those parts and upload it to Gradescope, or if you have a tablet, you can write directly on the PDF and then submit the PDF to Gradescope. And then and the R script, you will upload your R script file directly to CCLE, or I think Gradescope allows for people to submit code files as well. I'm not sure. I have to look at what Gradescope offers in terms of like uploading code. But anyway, this is definitely, you'll do the pen and paper part on Gradescope, and then the other part I'll figure out. Okay. To make sure your R results like line up with mine, and you know, if they don't line up with mine, then I'll check your script and stuff. Please make sure you have a current version of R. I think the current release is 4.0.3, but at least make sure it's 4.0 or later. Okay. And then I want to make sure you are generating the same random numbers that I am. So you would do set seed 1, RUnif6, and it should generate these exact numbers. Sadly, I mean, that's what I get every time I do set seed 1. Okay. All right. So these are the topics. Well, I don't know. Any questions on this before I go on with the topics, or does this kind of like the logistics part make sense to you guys? Okay. All right. So problem 1, Zoom link's the same. Yeah, same as the class Zoom link. Okay. All right. So part 1 is I will provide kind of a small sample of data that comes from some kind of specified distribution, right? And so it'll be the distribution is going to be one of these. I'm going to say, here's some data from the exponential distribution, or here's some data from the Poisson or binomial, negative binomial, gamma, or normal. Okay, so those will be kind of your choices here. And I'll provide the PDF of the distribution. And you will use the PDF and the data that I've provided to find the likelihood function. Okay, so you'll find the likelihood function of basically the data I've provided. And then I'll also provide the conjugate prior distribution for one of the parameters. Okay. And then using the data and the conjugate prior, you'll find the posterior distribution of the parameter. And then once you have the posterior distribution, you'll perform, so these parts are pen and paper, okay? And then once you have the posterior distribution, you'll perform Monte Carlo integration to estimate the expected value of a certain probability. So, you know, for example, like when we had the beta binomial, you'd find the posterior distribution of P, the proportion or the probability of getting a hit, okay, which was basically what we said was a batting average. And we said, and then we could use that to find the probability of getting 2 hits in the next 3 at-bats or something. So you would use Monte Carlo integration. And yes, I will post this document to CCLE. Okay, and then and you'll use R for that part. All right. Does that make sense? Any questions on this? I think you have a problem kind of similar to this in the homework. All right, you had a couple problems, right? You had I think in the homework there was an exponential problem, and then there was also a normal problem. The normal one was kind of a pain to figure out the posterior distribution. Okay, but you know, yours is open up. So, okay, do you need R for all 3 parts? No, you only need for problem 1, you only need R for the last part. Okay, this part you're going to do with pen and paper. The first 2, finding the likelihood function and finding the posterior distribution. Okay, problem 2 will be almost entirely on R. Okay, I'm going to provide some arbitrary function. You will estimate the integral of the function, okay, for a certain interval using Monte Carlo integration. So I've got a couple examples on the slides. You basically did that in your homework, all right? And then you'll also, and then I will say, so this part you'd sample from our uniform, and then I'll specify a different distribution to sample from. So I'll say like sample from this other distribution, it'll be a built-in distribution from R, okay? And then you will estimate the integral of the function using importance sampling, okay? And that's that, okay? So if you've done the homework, I think this part should be easy, okay? Or not easy, but at least straightforward, or at least familiar if you've done the homework. Okay. So, there might be, like in the homework, you had to adjust for, a proportionality constant, right? The ZR to kind of make sure the thing that, because so in the homework, you truncated the normal. So in order for it to integrate to 1, you had to multiply by a constant. Okay. So you might have to do something kind of like that. All right. Depending on, what the problem, how the problem's written here. Okay. All right. And then lastly, InverseCDF. I don't know. I might put these in different order. Okay. These will be the 3 problems, but they might show up in a different order. Okay. Last one, I'm going to provide an arbitrary PDF, and you will find the CDF. So you got to do some integration there. And then you'll find the InverseCDF. So that's some algebra. And then I will provide, so this one's done entirely in pen and paper. I'll provide some arbitrary values of U drawn from, our uniform, the random uniform, and then you will kind of plug those into the InverseCDF and tell me what values of X that these correspond to. Okay. And that's what I've got planned. That's we got 1 hour for all of this. For the script, I'm imagining just I guess I could give you I guess I can write an RMD template where at least you'll designate where your answers are. Okay, yeah, I'll make an RMD template. Okay. So so on CCLE, a PDF for the pen and paper stuff, and a RMD template, which will basically just be, put your answer to, problem 1, part 3 here, put your answer to problem 2 here, and that will basically be it. Okay. Questions on this? Any? The same format as 102B, where 1 problem per page. That's the plan, but you know what? On Gradescope, you can actually be flexible, and so I think I'll choose the flexible option where, if you need more than 1 page to answer the question, you can use more than 1 page, and you'll be fine. So, so if you need more than a page for a question or something like that, that's fine. And then Gradescope allows for that. Submission deadline will be 11. Yeah, probably I'll give you till 11:10. Okay, so 1 hour for the exam, and then 10 minutes for scanning and uploading, and any kind of submission things. Okay, but that 11:10 is a hard deadline. So give yourselves 1 hour, and then hopefully 10 minutes will be enough to scan and upload. Don't tempt the tempt the internet gods by working till 11:08 and then give yourself only 2 minutes to scan and upload. That's asking for trouble. So okay. All right. Is that good? Any questions there? Okay, so I'll post this. Maybe I'll just clarify a couple of things based on the questions that you've asked. So I'll say, there'll be an RMD file, and this and that. Okay. All right, so we'll go back to rejection sampling. Oh, let me give you your first quiz answer for today. What day is today? Friday. First quiz answer is E. E as in elephant. All right. Okay. What did I say? All right. Okay. Rejection sampling. Okay. So we want to generate a sample from some PDF F, right? Okay. We know the PDF of F, but we just don't know how to sample from it. Maybe we can't figure out the InverseCDF. All right. So we can't do InverseCDF method, and we're not able to generate directly from F. Okay. So what are we going to do? What we're going to do is we're going to find a candidate distribution, G, so just some other distribution that we are able to sample from. And kind of like importance sampling, there's some similarities between this and importance sampling, except importance sampling is used for estimating an integral, and this is for generating a sample. So anyway, you're going to find some candidate distribution G, and we are able to sample from G, okay? And the requirement is that the support of X, the support of F, sorry, which is X, the support of F must be fully contained inside the support of G, okay? Meaning, you know, wherever F is greater than 0, G also has to be greater than 0. And there has to be some constant, okay, such that M times G of X is greater than or equal to F of X for all values of X. Okay, so if you think about it, right? So G of X is a PDF, F of X is a PDF. Both of them have an area equal to 1. And so if G of X and F of X are not exactly identical, okay, then, and because both of them have an area equal to 1 and they both have at least, you know, G of X has, you know, the support of G of X is at least bigger than the support of F of X. So what that means is that there might be parts where G of X is greater than F of X, but then there will certainly be parts of G of X that are less than F of X. Because both of these functions, whatever they are, they both integrate to 1. So if there's a part where G of X is greater than F of X, then there has to absolutely be another part where G of X is less than F of X, if both of them have the same area. Okay, so what we need to do is we need to find some function M such that when I do M times G of X, it's going to be greater than or equal to F of X everywhere. So we're going to, or not some function, some constant M. Okay, and so the most efficient choice is the maximum value of F divided by G of X, right? Because if I divide G of X, if I take this thing and I divide both sides by G of X, I'm going to have M greater than or equal to F of X divided by G of X. Okay, so we need to have an M that satisfies this condition that M times G of X is greater than or equal to F of X. And the most efficient choice of M is going to be the maximum of this value and nothing larger. Okay, so anything larger than that is kind of an M that's too big. But anything less, an M that is smaller than the maximum of this, won't satisfy this condition. Okay, and so this is the algorithm for rejection sampling. You're going to generate values of X. These are our proposed values of X from G. And then you're going to calculate this ratio, which is going to be F of X divided by M times G of X. And this quantity will always be between 0 and 1 because M times G of X is going to be greater than or equal to F everywhere. So F divided by M times G of X will always be between 0 and 1. Okay, and then we're going to generate a random value of U. And if U is less than this quantity R of X, then we will accept this value X that was proposed. Otherwise, we're going to reject the x and keep going on. So let me do a couple examples of this, and maybe this will make sense. Okay. All right. So here's the PDF of the beta distribution. If you take the beta 2, with shape parameters alpha is 2 and beta 2, or A2 and B2, then you're going to get basically x to the 2 minus 1 and 1 minus x to the 2 minus 1. All right, and then the normalizing constant is 6. Okay. Now we could, technically this is a little silly because we can sample directly using R beta, and we can also figure out the inverse CDF. Okay. But for this example, just for the sake of our learning, we're going to use the inverse CDF. All right. And so the support of f is this interval 0, 1. Okay. And so for our candidate distribution, we're going to generate values from the uniform. Okay. And that has a PDF equal to 1, and its support is 0, 1 as well. Okay. So the support of G is compatible with the support of F, and that works. Okay. So this is what it looks like. Like if I take the integral, so f of x, which is the beta distribution, beta 2 distribution, has this PDF in red, and the uniform distribution has this PDF in orange. Okay. And if I integrate both of these, the area underneath the orange line is equal to 1. The area underneath the red curve is equal to 1. Okay. Now what we need to do is we need to find a value of m to multiply by g. Okay, so the uniform is g, and we need to multiply this by m so that the function m times g is greater than f everywhere. Okay, and so just visually, what does it look like m needs to be? You can throw it in the chat or speak up. Yeah, just visually, it looks like it's going to be 1.5, and indeed, that's going to be the answer. Okay, because the max of f is at 1.5, so we need to take 1.5 times 1, and then we'll get up to 1.5. Okay, so we could do a little bit of math. I need to reformat my slide here. Okay, so the most efficient choice of m is going to be the max of f divided by g. Okay. So f is 6x times 1 minus x, and g is 1. So f of x divided by g of x is 6x times 1 minus x divided by 1. And then to solve for the max of f of x over g of x, okay, I'm going to just take the derivative of this. Derivative is 6x minus 6x squared. I get 6 minus 12x. We solve for x. X is 0.5. So the max occurs at x equal to 0.5. And then when I plug that in, 6 times 0.5 times 1 minus 0.5, the maximum of f of x over g of x is 1.5. So indeed, that's going to be the choice of m. Right? So, just visually, we can see that, yeah, we need to multiply 1.0 times 1.5 for it to be bigger than this. And when I go through the calculus, we also get 1.5 here. All right, and then so if I multiply the orange line, or if I multiply g times 1.5, which is what I have here, so f is in red, okay, g is in orange, and then m times g is in blue. Okay, we can see that the blue line is at least equal to or greater than the red line everywhere. Okay, now I could pick an arbitrarily large value. I could pick like m is 100, and it would not be an efficient choice, but it would satisfy. Okay, so this is what we have here. Okay, and now we run the algorithm. Okay, which is my proposal distribution is g, which is uniform. So I'm going to propose values of x from the uniform distribution, 0, 1. And then that ratio is going to be f divided by m times g. Okay, so I take g of the proposed value. This is the PDF of the uniform. So that's basically just 1. Okay, and this is going to be 1.5 times 1. So technically, this is a little bit silly, but this is just the general form. So this is 1.5 times 1 down here, and then f of x is going to be basically the upside down parabola there. And okay, and then I generate another set of random values, random uniform values, u, and we're going to accept the values if u is less than the ratio r underscore x. Okay. And then the accepted values of x are going to be basically the subset of the proposed values where accepted is true. Or accepted is true. Okay, and so if I take accepted x and I create a histogram of it, the histogram's in gray, and if I overlay the beta 22 density, we can see that we've done a pretty good job of generating values from the beta 22 density. Here is the plot of the theoretic CDF in red. Okay, P beta is the theoretic CDF in red, and I've overlaid that with the empirical CDF of my accepted x values, and we see also pretty close match there. Okay, and this is kind of a diagram showing basically values that we've proposed and whether it was accepted or not. Okay, and so what I've got going on here is it proposes this in red, or in red and black. All these dots are kind of values that it proposed in the uniform. And the vertical is basically, did we accept that value or not? Okay. And so we basically go from 0 to 100%. Okay. And so in regions where near 0, like if we propose, so the uniform distribution will propose values like 0 just as likely as values like 0.5. Okay. But if it proposes a value like 0, okay, the beta 22 distribution says it's almost never a value like 0. So the only way it's going to accept a value near 0 is if the u value comes in less than that ratio, which is f divided by m times g of s. Okay, and so so what we see is that a lot of times those u's came in a lot bigger, right? So if u came in right here, it's not underneath f divided by m times g of s. Okay, whereas these dots represent values where u came in under f times m times g of s, and so these values were accepted. So this represents everything that was kind of proposed. I actually proposed like 100,000 values, which would have just covered the entire grid with dots, and it would have been too hard to read. So I'm just looking at the first 300, and so out of the first 300, this kind of represents the values that were proposed along the x-axis, and then whether it got accepted or not is if the uniform value came in underneath the curve. And so if it came in under the curve, it was accepted, and then the red values kind of represent values that were rejected. So we're basically just kind of isolating ourselves, like at, at point 2, we say, well, how often should we accept one of these values? And, we're going to accept looks around 2/3, and we reject around 1/3 of them. Is that all right? Okay. So, so the empirical acceptance rate is going to be how many values we proposed, how many values we accepted divided by how many values we proposed. So I'm taking the length of the accepted divided by length of proposed. Can I go back to the code where I made the proposed x? So I proposed x from R uniform, 0 to 1. Okay, so I proposed x from R uniform, and then whether I accept it is based on whether u is less than or equal to this ratio. And so when I plot this, I'm plotting the proposed values against basically u, times m to kind of fill out the this thing. Okay, so so out of the 100,000, I accepted 66,658. The theoretic acceptance rate is going to be 1 over m. Okay. F and g are both PDFs, which means the integral of f and the integral of g are both equal to 1. The integral of m times g of x is going to equal m, right? So if the integral of, if g is 1, the integral of m times that is going to be m. And so therefore, you know, what portion of kind of all the proposed values, this is kind of the proposal region, is covered by f of x is going to be 1 over m. So the theoretic acceptance rate is going to be 1 over n, which in our case is going to be 2/3. Right, so the total area covered by the blue line is going to be 1.5. Total area covered by a PDF is 1. So it's going to be 1 divided by basically 1.5. All right, so that's that one example. Here's another example. All right, let's see. Okay. Question, is there no way to sample an exact number of samples from the distribution since there's no way how many values will be accepted? Yeah, it is not possible. So I guess you can run a while loop until you get the number of samples that you want. But if you need like 10,000 values and you know your acceptance rate is around 2/3, then you'll probably need to propose something around 15,000, but that doesn't necessarily mean you'll get exactly 10,000. You might get a little bit more or a little bit less. Okay. So a good acceptance rate is basically as high as you can get it to be. But, you know, so, you know, the closer you can get between, you know, closer to 1 is better, but that might not be an option. Okay, so there's not, when it comes to rejection sampling, we don't necessarily have a good or bad. It's just you take what you can get. All right, and sometimes you can think of a distribution that will work well, and sometimes you don't have a good distribution. Okay, so here's another example. Let's say we want the PDF to be sine of x for x between 0 and pi over 2. Okay, and so this will integrate to 1. Okay, sine of x on the interval 0 to pi over 2. Okay, so that's basically you know, the first 90 degrees of the circle. That integrates to 1. Okay, and so for a candidate distribution, we'll use the uniform distribution from 0 to pi over 2. Okay, so we'll have kind of the same thing. And so the PDF of this distribution is going to be 2 over pi. Okay, because this thing has to integrate to 1. So 2 over pi times pi over 2 will give us an area of 1. Okay, and so we have to find an m such that m times g of x is greater than f of x for all x. Okay, so the maximum value of f of x is 1. Okay, and so the maximum value of f divided by g of x is going to be 1 divided by 2 over pi. So m is going to be pi over 2. All right, so let me just kind of show you what this looks like. So red is the sine curve. And then pi over 2 is this value. But if you multiply, so this is our proposal distribution. We're going to generate values uniform from 0 to pi over 2. Pi over 2 is around 1.5. Okay, a little bit more than that. 3.14 divided by 2. It's like 1.57, I guess. Okay, and so you know, 1 divided by 1.57 is, you know, around 0.6 something. Okay, and then if we multiply that by pi over 2, then we get the blue line, and the blue line is always going to be greater than the red line. And so so here is our algorithm. This time we're proposing values from the uniform distribution from 0 to pi over 2. Okay, these are going to be your proposed values of x. And the ratio of whether we accept or not is going to be f divided by m times g. Okay, where g is now, so this is basically dividing by 1. All right. Now, right now, it seems a little bit silly because m times g has always been a constant, right? M times g has always been this blue line, which is a constant. In this case, it's 1. M is 2 over pi. I'm sorry. M is pi over 2, and g is 2 over pi. So, you know, this constant is just 1. So whether we accept or not is going to just be f of x, okay? Because this simplifies to 1. But this will work in general as well. And then I'm going to generate a bunch of values from the random uniform from 0 to 1. And if u comes in less than r of x, okay, where r of x is basically the sign of the proposed x value, okay, because f is the sign of x. Okay, if u comes in less than that, we will accept it. And so when we look at the histogram of the accepted values, it fits what we want. This looks like the sign of x here. Okay, and if we look at the empirical CDF versus the theoretic CDF is 1 minus cosine of s, or cosine of x. Okay, that also fits. And this is kind of the diagram. And again, we're generating values uniformly from 0 to 1.57-ish. And we will only accept it if a random uniform value, which is kind of the vertical spot, comes in underneath the line. Okay, and so this is why our histogram ends up looking, like the shape that we want. Okay, and so the proposed the points are located at u times m times g of the proposed values there. Okay, and so that's that. Is this so far okay? All right, so this last one, for whatever reason, I couldn't get these slides to knit, okay? So this time, we're not going to use a uniform proposal. We're gonna have an exponential proposal, okay? So here I'm gonna do the folded normal. We saw the folded normal earlier, but so it's basically just the positive half of the normal distribution. And because it's the positive half, the PDF is going to be 2 times the PDF of the normal distribution. And so for our candidate distribution, we're going to take just the exponential with rate lambda equal to 1. And so its PDF is e to the negative x, right? And so so we look at this, the support of g is x greater than or equal to 0. The support of the folded normal is also x greater than or equal to 0. So these supports are compatible with each other. So we can do this. Okay. And what we need to do is we need to find an m such that m times g of x is greater than f of x. And the most efficient choice of m is going to be the maximum of f divided by g. And so here is the plot of f. F is in red. And our proposal, g, is in orange, okay? And so now I need to find a value such that I can multiply the orange by some constant so that it's always going to be greater than the red, okay? So we have to figure this out. And I don't know why I couldn't get the slides to render. So so here, I don't know if you guys can see this. What we want is we want to find the maximum of f divided by g, okay? So here I have the PDF of f, okay, which is 2 divided by root 2 pi e to the negative x squared over 2. And then the PDF of g is e to the negative x, okay? I don't know if I can make this any bigger. Okay, and so here, I've got e to the negative x squared and then e to the negative x. So this becomes e to the negative x squared minus x in the numerator. Okay, e to the negative x squared minus x. And so the maximum of, oh, this is the problem. Now it will render. I was missing a curly brace, I think. Okay, well, we'll see. Look at that. Now it rendered. Okay. Curly brace, curly brace. All right. Okay, this is, okay, well, I'm happy now. All right, so when you combine this, this is what we have here. Okay, I got to format some stuff here. But so the max of this, okay, I've got e to the negative something. Okay, so the maximum of e to this, right? This is just a constant, is going to occur at the minimum of x squared over 2 minus x. Right? And so I skipped this part, but with a little calculus, you can see that you don't even need calculus. You can just graph it or whatever, right? You can just think about this. The minimum is going to occur at x equal to 1 here. Okay, so the maximum of this is going to be at the minimum of this, and the minimum is going to happen at x equal to 1. And if you plug in 1 into this, you're going to get m equal to 1.32. All right, and so if you round up, always round up because m needs to be at least greater than this. So we round up and we get m is equal to 1.32. And so if I plot that, okay, so the original curve in orange is this. And if I just multiply the orange by 1.32, right, so here g of s is in orange, okay, and if I just multiply g of s times m, so I have m times g of s, in blue, we can see that the blue line is always greater than or equal to the red line. Okay, so the red line represents the PDF of the normal distribution, which is, I just cheated and I just use the f is 2 times the normal density. Okay, I'm just using r's normal density function. And then g is the density of the exponential. Okay, so if I do 2 times the normal density, I get the red line, and then blue is m times g of s. Okay, so we can see that the blue line is greater than or equal to the red line everywhere. Okay, so the algorithm, this code has pretty much been the same here. Okay, the only thing that has changed each time is how I'm proposing the x values. Okay, so here I'm going to propose n values from the exponential distribution. Okay, default is rate equal to 1. So the proposed x come from the exponential distribution. And then whether I accept, this ratio is going to be f times the proposed x. So that's going to be, what is this red, for the proposed value, what is the red line equal to? And I'm going to divide it by basically the blue line. And so whatever the red line is divided by the blue line is going to be a basically a value between 0 and 1. All right, and so that that's our ratio. We're going to generate some uniform values from random uniform, and we will accept if u is less than that ratio. Okay, so this is going to be a vector of true falses, and so the accepted x values are going to be the proposed values subsetted to the accepted. Okay, so if I plot the histogram, this matches what we want. Okay. When I plot the empirical CDF, okay, which is 2 times p norm minus 1, it also matches, so that's good. And then this is kind of a plot of what we have. So it proposes values from the exponential. Okay, so the exponential distribution sometimes proposes values like 4 or 5 or things like that, but we can see that rarely do those fit underneath the red line. Okay, and so in areas where the exponential proposes too many, some of those get rejected, and and in other cases where it fits under it, it matches. So, so this is kind of the picture that we get. Compare, we're proposing values in blue, and then we're only accepting the ones that fit underneath the desired density here. All right, let me give you the last. I think I need to give you 2 more quiz answers. Is that right? Okay. Okay. Last 2 quiz answers are B and A. So bear and apple. B and A. B and A. Okay. We will end there, and I'll fix up these notes and slides and get them posted. And good luck as you study, and we'll see you guys on Monday, either at 10 a.m. or 10 p.m. for your first exam. Okay, right? Same Zoom room. Okay, see you guys then. Good luck. Have a good weekend.